All right, so the first thing I should note here is that this basic idea was originally proposed to me by Eric Holloway. I told him he was nuts. I then changed my mind and made this presentation. Hopefully dealing with the issues that made me think Eric was nuts. Let's see if I accomplish that. But essentially the question that I was looking at is that we'd like to think that things engineers create or humans in general build or design can somehow be distinguished from things that aren't designed as such. So we have, for example, Mount Rushmore versus a random mountainside. Those, of course, are made up of pretty much the exact same physical components, but somehow we'd like to say that Mount Rushmore is quantitatively different than a random mountainside. But it's difficult to put any sort of mathematical or any sort of precise formulation on that concept. Similar idea if you've got a beach versus a beach where someone has written in sand. Intuitively, we're pretty sure those are quite different, but it's really hard to quantify that. So that's essentially what I'm looking at here. So the basic idea that I look at, the question of design detection and the challenge to it there, as well as the proposed solution, and I'm going to work through some examples to try and explain what I'm doing. So the question we ask is, how do we infer design? How do we say that something is designed or has information? According to Bill Lensky in his book, The Design Inference, the answer is specified complexity. That is, you need to have these two different components, specification and complexity. The first of these is complexity and asks the question, is it improbable? We basically ask, is this event improbable? Because if it's a probable event, we would never attempt to say it's designed. That would be pointless because it happens by random chance all the time. Most of the evolutionary informatics lab where I work has actually worked in the area of probability, basically asking whether we can cleverly shuffle things around and make things work out better for us. And we basically say, no, shuffling dice doesn't really change your situation all that much. Which brings us to the other side, which is specification, which is defined as conforming to an independently given pattern. The problem here is there's not really a precise definition there that you can actually apply. So it's somewhat fuzzy there. I can't quantify it. I can't put a number on your fittingness to some independently given patterns. And finally, it's difficult to maintain that requirement for independence. So to explain that, the notion here is that it's really easy to hit a bullseye if you're allowed to paint the target after you fire the arrow. All right? So, but it's only fair to consider a bullseye hit if you fired the arrow after the bullseye was painted. That's why you have a requirement that the specification be independent. But the problem is that when we're looking at many objects of interest, we can't do that because we're always picking our target after we've looked at whatever we're interested in. So for example, if we're looking at life, we say, well, life is a self-replicating system. That seems like a useful pattern, but we're only interested in self-replicating systems because we've seen them. We would have never defined that as our specification if we weren't living in a universe with self-replicating systems. And the same for pretty much anything else you could consider, say, a flying animal. You would not be interested in flying animals unless you'd seen birds. So the problem is that we can't actually define an independent target in pretty much any circumstance. Which leads to the proposed solution, which is to use Kolmogorov Complexity. Because this is something we have in theoretical computer science to measure the degree to which something follows a pattern. Now it's defined as the minimum program length required in order to describe an object. That may be too theoretical for most people. But so in more lax terms, the question is how many words would it take you to describe an object? To explain further, we can look at some examples. Firstly, we have in the top left corner, we have a very simple object. It's just a bunch of black squares. So I can describe that as black repeat. So it has a very, very short description, and we therefore say it very much follows a simple pattern. And I would argue it is therefore specified. If we look at the next one down in the bottom left-hand corner here, we have a checkerboard pattern. Now I would take slightly more words to describe that because I would have to say black, white, repeat. And so it's going to take me more time to describe that, and as such, it's going to be less specified. And we can continue on to the top right corner. I would have to say 5 white squares, 5 black squares, and of course in there you can't tell that they're separate squares, I'm sorry. Repeat. and it's slightly longer, slightly less specified. And so we can see that there's a sliding scale of how specified something is depending on how well it follows a pattern. And the last one there, unless I failed in my attempts to be random, doesn't really have any sort of pattern that you can describe. And if I were to try and describe it, I would have to describe each individual square. I'd have to say it's black, 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 white, black, etc. And I have to go through the whole square, and that would take a lot of time, and thus I can't compress it. I can't give it a short description, and therefore we would say it's not specified. And so that's the basic idea of using Kolmogorov complexity to account for specification. But there's a problem, and that many things that we think of are specified don't really fit into those simple describable patterns. You have stuff like an English sentence. I can't really give a really simple pattern that describes this English sentence, yet that's exactly the kind of things we want to say are specified. I also say if I was looking at the design of the building, there's going to be some regularity to a building design, of course, unless it's this building. But I still cannot reduce the building to a really simple pattern like I want it to be in order to describe it as specification. And the same, say, for this electronic circuit, which does zoom as well. I can't reduce that to a really simple pattern, which is why we introduce the context and conditional Kolmogorov complexity. Now, technically, this is described as running a Turing machine with input on the tape. But what it basically means is that in addition to describing a pattern from scratch, you have some sort of context of things you're allowed to draw from. So your context could be the English language, and then you're allowed to pull things from your knowledge of the English language to describe the pattern. And so it'd be like if you were in a calculus textbook. The calculus textbook is going to assume that you already know algebra, right? And if the calculus textbook had to explain algebra before teaching you calculus, it would take a lot longer. And so it's actually you can provide a much more compressed version of calculus by virtue of assuming you have a certain context already. And that expands what we can describe. Now, to explain how that helps with the previous examples, we have a big circle. So this big circle here represents everything in the scope of whatever kind of objects we're currently trying to describe. So this could be, say, all possible combinations of English letters, or maybe it's all possible constants for the universe. And it would take me the log of the size of omega bits in order to describe an individual element from the thing, so an individual combination of letters or something. Right? But what we can usually do in cases of specification is we identify some sort of smaller set that has some interesting property. And here I'm calling the set S. And because that set is smaller, it takes me less bits to describe an individual element from that set. The idea is that as long as I can give a simple description of that small set, that it actually does let me to compress it. So here's just some examples of things that could constitute a description of that smaller set. So it could just be all the things that are actually valid English. Much smaller, and thus I can compress it, or royal flushes, or any of these other sort of constructs that somehow describe a property true of some small fraction of all the possible items. And if I can use that, I can always actually get specification and compression out of it. Now, this is going to come at a cost, of course. The K stands for Kolmogorov, and the K of S then means how hard is it to describe this subset. And the log of the size of S is how much it takes to describe an element in that. So that gives me the compression length of a complete element, and thus I can describe it without having to spend the whole log of omega bits. To put that together, we have this, which I'm calling algorithmic specified complexity, because everything with an acronym is better. Now we note on the left-hand side we have the complexity term, which we're saying is the negative log of probability. Now the probability here is merely a parameter that's being put into this equation, and I'm not making any assumptions here about what an accurate probability distribution would look like. All I can actually do is I can say if this number is really high, either a really improbable event happened, or you have the wrong probability distribution. And then the K of X, you can see there, that's the description length required to describe the object of interest. All right, so to look at some examples, the first thing we have is some basic English text. Here we have the quick brown fox jumps over the lazy dog. You've probably heard the sentence before. And so I'm going to encode it here in something called UTF-32, which I've chosen merely because it's an encoding which lets me encode letters from any alphabet in the entire world, pretty much. And so using that particular encoding, it would take about 1,400 bits to describe this sentence. If I have the context of the English alphabet, so my program that I write to output this is allowed to take into account which letters are actually in the English alphabet, then it only is going to take me 204 bits to describe it. And if we assume that the sentence was generated by flipping a coin for each of the bits in the input sequence, that gives me 1,000 bits of algorithmic specified complexity. Or basically, we've got a pretty high confidence that this sentence was not generated by flipping coins to choose bits in UTF-32. Right, but that's assuming a particular probability distribution. If instead I suppose that the sentence was generated by picking letters out of a hat, the situation changes because the sentence is much less complex then. Because I don't have to explain why we got English letters out of the set of all letters, because I've already explained that in the probability distribution. And what happens then is that the compressed length and the complexity actually pretty much cancel each other out, minus this constant. Now the constant is that because basically in algorithmic information theory, there's some parts of the program we can give you how long the program's going to be, and other parts we really have no clue, so we say, oh, it's a constant. Which is a little bit of a cheap trick, but we do it so. But so basically, the measure ends up minimizing at about this negative constant point. Of course, if we expand the context, we can change the situation again. So if we introduce the Oxford English Dictionary, so now the program's context is not just it knows which letters are in the English alphabet, we also know which letters are in the English dictionary. And by doing that, I can actually compress it further to 167 bits, and I can thus get 40 bits of algorithm specified complexity. Now, of course, if I were to suppose now that someone were choosing random words from the Oxford English Dictionary, then I could get rid of this specified complexity here because the probability distribution would again explain what I'm seeing. But as long as we don't have that distribution, we can say that this distribution is not a good explanation for the sentence we're looking at. To jump over to the opposite side of the spectrum, something that shouldn't be specified would be random data. So in this case, we're going to generate data by flipping a coin 1,000 times and putting a 1 for every head and a 0 for every tail. It's of course going to take 1,000 bits to write that. Fundamental result from algorithmic information theory is that if it's random, we can't compress it. We have to just write out the whole thing, plus a constant to say write this out. And if we assume that our distribution is uniform, then we end up with the same value. We basically have no reason to reject that distribution as legitimate. However, we could also consider the case where we've got a biased coin. So we've got a coin that actually is going to land in heads 2/3 of the time because it's weighted. In this case, we actually can compress the length. So it's actually not going to take me full 1,000 bits to describe it. I can describe it in less. The process by which that works is really fascinating, but off topic here. But basically that means that I get 81 bits of algorithmic specified complexity. Now this is despite the fact that in some sense this is random data. It was generated by coin flips. Because all I can really do is say, well, this distribution doesn't explain the data very well. This particular element I'm looking at defies explanation as that. Of course, if I change the distribution to the actual distribution of the biased coin, then the complexity will drop and I'll end up with negative C again. All right. Cards are interesting because I don't have to worry about the fact that I've got the wrong distribution. Because if your card hands were not generated by uniform distribution, it means somebody's cheating. All right? So I don't have to worry about there could be some other proper distribution. But here I've looked at various different poker hands. We know that each poker hand has a number of different ways of showing up. All the way from a royal flush, which has 4 possibilities, down to a pair which has some million possibilities. And we know that the complexity of every card hand is the same. Right? Because every card hand is equally improbable. And this is a favorite claim of people trying to dispute design inferences to claim, well, you can't claim that because that's like claiming something special with poker hands, when all poker hands are. Every poker hand is really improbable. Because you also have to take into account specification. But what changes for these different elements is how much time it takes me to describe the hand. So for a royal flush, I can describe it as a royal flush of hearts. I can't just describe it as a royal flush because it's actually 4 different royal flushes. So I have to be specific which one it is, which is why by my calculation it takes 5.3 bits. If you go all the way down to, say, a 1 pair, that's going to take me 21 bits because I basically got to tell you each individual card that I've got a 3 of spades and a 6 of diamonds and a 10 of clubs, etc. So it takes me a long time to say that. So it's not very specified because it takes a long time to describe. Which means that we can put them through the formula and we suppose that there's 16 bits of algorithmic specified complexity in royal flush because it's pretty rare. And there's nothing whatsoever if you're getting something like a 1 pair. Of course, if you've got just 1 royal flush, you might not be suspicious. I mean, I've never seen one, but I figure if you play poker more than me, which is twice a year or something, you might see them. But what happens if someone keeps getting royal flushes? And so this is what happens is as we keep getting royal flushes over and over again, the specification increases by about 21 bits each time because that's the number of bits required to specify each individual hand in terms of complexity. However, it only takes a couple of extra bits each time to describe your hand, because all you have to do is describe which of the 4 royal flushes you've got. So because the complexity increases rapidly and the compressed length increases slowly, we end up getting a substantial increase of the algorithmic specified complexity, telling me eventually that someone is probably cheating, and so you tell the dealer that he's cheating because his specified complexity is too high, and he looks at you strangely because he doesn't know what you're talking about. All right. We can look at protein. According to Doug Axe's work, 1 in 10 to the 64 proteins successfully fold. So if we can describe a protein as folding, that restricts us to a much smaller set than the original set, and thus we can compress it. The idea here is that the context we can assume is the law of physics. Now we can't include folding context because that would be sort of introducing that dependence we're trying to get away from. But it seems pretty safe to introduce the laws of physics as a context. So that gives me the 787 bits to describe a folding protein as opposed to just any protein. And we have that plus C. Now inside that C is going to have to be a description of what it means for a protein to fold. And if we assume here that we're just picking random bases uniformly, of course that would not be the Darwinian explanation that the distribution is random, is not going to be uniformly random. They'll have some other distribution. I'm not worrying about that here. So then we'd say that there's 212 bits of algorithmic specified complexity, or in other words, we've got really good reason to suppose that this protein was probably not generated by randomly choosing bases. All right, you also have the interesting case of Kirk-Durston et al. Have defined something called the functional sequence complexity. And as it turns out, that's a special case of the algorithmic specified complexity, because what they're calling the null state, we're calling complexity, and they take the number of sequences, and what we're looking at as the specification. And so as it turns out, the algorithmic specified complexity is less than or equal to the functional sequence complexity minus a constant. And that's that annoying constant that keeps showing up everywhere. So here's values that Kirk-Durston et al. Have calculated for functional sequence complexity, and thus they're also approximations of an algorithmic specified complexity, because they describe a protein which has some particular functionality. And so if we can describe that functionality, we can get to that smaller set and thus have an easier time describing it. All right, possible concerns. This is the original reason that I told Eric he was nuts. All right, so the issue is that if you go back to Dembski's explanatory filter, he has this notion of necessity and of law-like processes. And the idea is that we don't want to infer design on things that we can easily appeal to natural laws. So for example, in the initial picture you had a beach. And a beach actually follows a very nice sloping simple pattern. And thus it is actually very, very specified under this definition, which could seem kind of problematic because no one is going to try and make a design inference about a beach. Right, but what we would say here is, well, actually the issue here is that beaches are very probable given the laws of nature, and thus they're not very complex. So yeah, they're somewhat specified, but that's counterbalanced by the lack of complexity involved there. But the question is, does this mean that everything that's specified is also going to be amenable to being explained by law-like processes. And there's several things which suggest that's not really going to be the case. One is that the real world in many cases doesn't seem to really follow algorithmic distributions. If you look at the chirality of proteins, for example, they've all got to be left-handed. That's a really simple pattern, but as far as we know, natural processes don't really seem inclined to produce that unless you're really helping them out. You also have the question of context, which is going to make the situation different, because if you're taking into the context of English, say, your specification, and the wind and waves are not going to be taking into account English when they're deciding which probability to form on the beach. So that would make it different. But I think one of the big things is that time matters in the real world. Algorithmic information theory is known for the fact that, well, all of computer science is known for the fact that if some part of the real world ignores it, is annoying, we just ignore it. And so in Kolmogorov Complexity, it doesn't matter how much computational effort it would require to get somewhere. So if you were to, say, design a boat motor, you would have to give complete specifications for your boat motor. But as far as Kolmogorov Complexity is concerned, describing it as a boat motor is good enough. So leaving you it's free to leave you as much effort as you want in order to actually complete the job, but that's not really going to apply if you're trying to figure out the probability distribution in the real world. Another concern is that the context is arbitrary, but this seems somewhat to the degree of how our perception of information works. If I look at Arabic, it looks like someone was scribbling. Now, I'm sure that that's not what Arabic is. I have faith on that issue. But I don't have the correct context to understand it. So it seems that all information perception is based on having some sort of context that you can actually identify. So that seems to be there. It is, of course, important to not pick a context somehow based on what you were trying to identify, or else you can make anything specified. So you've always got to pick a context which I think is somehow prior to the object that you're investigating. The other thing is that you can't actually compute the values, because one of the fundamental results of Kolmogorov Complexity is that you can't actually write a computer program to compute the value. And it's actually related to all of those questions Jonathan was talking about that you can't do. Computer science people sit around proving things they can't do. I think this shows we have too much time on our hands. But you can upper bound it, so I can say that it's at least this specified, but I can never prove that I've identified all the specification in an object, which I think is actually what you would expect to happen, because if you don't know the functionality of something, you would expect to be able to identify less specification than after you've identified the functionality of it. So this does actually seem to fit with how it works. It does have practical things like those constants and other mess, which suggests that it may not be a really practical way of measuring anything, so much as perhaps a theoretical underpinning for various, perhaps more useful devices. So the conclusion here is that design is inferred by complexity and specification. You have to have both of these in order to infer some sort of design, and suggesting that specification can be measured by looking at the conditional Kolmogorov complexity. Okay.
You've reached a conclusion, but I'm not sure what the significance of it is. I'm assuming this is the first part of something that's going to continue. What would be your next step?
What would be the next step? Well, if I knew what I was doing, I wouldn't do research. So, I mean, sort of just right now looking at the examples and seeing how well this actually works with the sort of idea of trying to measure this notion of specification. And sort of, I think at this point, the idea would be to expand it a little bit into more examples, and then seeing if there's any interesting mathematical results that can be proven about it. John?
One thing that seems to be a real interesting application to it is, for example, if you do natural language processing, you could infer what context someone is most likely to be using. So if engineers use a different context than artists, then you might be able to infer a context and do better natural language processing.
That would work great if we could actually calculate Kolmogorov complexity. Dr. Stitch.
It's okay.
I was going to go snitch, but no, that wasn't right.
Okay, you guys all know I have a kind of hobby horse that I ride here. So instead of a hobby horse, I'll try to drop a fly doing backstroke into the ointment.
Okay.
I'm going to read to you a response from information theorists responding to Dembski's view of things in his omega space that he has, that you flashed up there. Quote, "We have no objection to natural language specifications per se, provided there is some evident way to translate them into Dembski's formal framework. But what precisely is the space of events of omega here?" Now, what that means in plain English is these critics of these information theorists, critics of Dembski, are saying that meaning and functionality, which are the two components of intelligent design's vision of design, are mathematically ambiguous. These are information theorists, not me. Information theorists that are saying that meaning and functionality are ambiguous things. Let me give you a simple example for functionality. A pair of pliers, a nutcracker, an insect's mandibles, and a lobster claw all have one and the same and exact functionality. That is, applied to different situations. That is, to hold tight and possibly crush an object. Yet, their complexities exceedingly vary. Now, that's exactly the point. That's exactly the point where the mathematical reductionism that's inherent behind this fails. The math can measure the information, but nowhere has either Dembski or Behe or Stephen Meyer or any of those guys, to the satisfaction of the information theorists, and certainly not to the, and I don't mean to be flying a flag here, but certainly not to the satisfaction of Thomists or other philosophers of nature. Nowhere have they rigorously demonstrated the very question that I asked of Jonathan. Rigorously demonstrate that meaning and functionality are measurable, meaning applying a metric to quantities.
I mean, to some degree, that's what this is trying to move towards in the notion of describing form complexity. Because if I can describe something as functional, then I can actually compress it. What I mean is that if I look at pliers, there's a bunch of, if I were to write together the specifications for how to make pliers, that would take some amount of space. Under Kolmogorov complexity, I don't have to describe completely what pliers are. I can say, well, pliers are objects which successfully hold things. Now, of course, there's lots of things that qualify under that, but I can then specify which of the many different objects that can successfully hold things I'm actually referring to. And this idea is that would actually take me less space in terms of a computer program to describe than actually describing the complete pliers thing. And that is what the notion, and the idea is that the space I save is a measure of how much specification, where functionality is a subclass of specification.
But they would respond precisely to something that you just mentioned. They would say, you just made our point. When you said just a minute ago that you don't have to know what pliers are, you've basically stopped the discussion about the functionality and in fact what the thing is that you're describing. They would go with you 100% in terms of what you're trying to measure in terms of the information content. But as soon as you try to impose a meaning, in other words, what pliers are, what insect mandibles are, what pincers are, what rib spreaders are, and all this other stuff, they would go, well, wait a second. How can we have a conversation to describe what we're trying to go to if, as you just stated, we don't have to know what they are?
No. You do have to know, but I don't have to tell you. What I mean is that the question is how hard is it to describe the object? I don't have to describe, I don't have to describe completely to you what pliers are in terms of their physical layout, if I can get away with telling you what pliers do, which is easier. The theory is that the amount of space I say indicates a quantifiable notion of specification, because the functionality allows me to compress it.
Which they would say, immediately following that, mathematically ambiguous.
Kolmogorov complexity is not mathematically ambiguous.
Functionality is mathematically ambiguous. You can't capture mathematically what the function of insect mandibles, pliers, and so on are. You're talking about the essence, the meaning of something. And again, there's never been a demonstration that you can do that you can jump that gap from information content, complexity, compressibility for storage of that information, and so on. Everyone follows these guys to that extent. But then they make the leap to the meaning and functionality as if it's just, yeah, of course it's that way. We're ready to listen to them, but to this day, and it's not just me, I mean, I read this stuff, I follow this stuff very closely. To this day, they haven't responded to those questions. I'm not, please don't misunderstand me, I'm not criticizing your work. I'm not.
I know.
Trust me, I'm not criticizing your work. I'm not, please keep on going. What I'm saying is probably what Professor may have been intimating. Where are you going with this? Because if you're staying within the realm of information theory, fantastic. Please continue to do the good work. But if you're going to jump to something like meaning and functionality, you have to demonstrably, show that you can actually go there, that you can cross the gap from a mathematical description to something that is rich with meaning. Okay?
I mean, that was some of where I was getting at a little bit with biological examples of a folding protein, which I would argue is a small example of some sort of functionality, as well as with tying it to the functional specified complexity, which is also an example of that. I haven't developed that perhaps enough to satisfy critics, but that is sort of the idea, I think we can actually mathematically describe functionality.
Okay, I'm not going to chase it, but it's something to consider.
Right. Eric?
I had a recommendation for a future direction you could go. You said that while Kolmogorov complexity is not computable, you can approximate it. And so if you approximate Kolmogorov complexity, while that won't necessarily tell you whether something is not designed, it can still give you a dependable indication that it is designed. And that follows the characteristics of the what's it called? The filter thing. Whatever.
Sure.
Explanatory filter, correct. So it guarantees you true positives, but it doesn't guarantee you true negatives. So in that case, if you can approximate Kolmogorov complexity, you can do that algorithmically. And so then you actually have an algorithmic metric you can use.
Sure. That's too practically minded for me.
Yeah.